going to go ahead and continue our work with graphing simple rational functions. So yesterday we looked at the parent function of 1 over x, and we noticed that there was both a vertical and horizontal asymptote for this function. And what we're going to look at today is how we can tell where the asymptotes are by looking at our equation. So I'm going to go ahead and pull up Desmos. And I have our parent function here. We want to just notice that our asymptotes, again, are at x equals 0. And we also have a horizontal asymptote at y equals 0. So if we were to go ahead and make our denominator have a different value that produces 0, so for example, x minus 2, we now know if we plug in 2, that would produce an undefined value for our denominator because we would have a 0. So now we can see that 2 is actually going to be at our vertical asymptote. Again, and the reason why is because if we were to plug into our equation, we get 2 minus 2 is 0, and that's undefined. Another thing I want to explore, is if we add a value. Right now we can see that we're centered at the origin. So what happens if we add a value to our function? Sorry if I create plus 5. That makes a little bit more sense. Notice how our entire graph shifts up 5 units and our horizontal asymptote has moved with it. So now we can see that our horizontal asymptote, instead of being at 0, is now up here at 5. So we can tell where our horizontal asymptote by this value that's added at the end of our function, and our vertical asymptote is where our function will yield a 0 in the denominator. So let's go ahead and look at an example in our notes, and we'll graph one together. So here we have g of x is 3 times 1 over x minus 1 plus 2. So the first thing we notice is that we have a vertical and horizontal asymptote, and we can tell that our function has moved a little bit. So we're no longer centered at the origin like we are with our parent function. So the first thing we notice is that we have a vertical asymptote, and we can see where that is by looking at where our function will yield a 0 in the denominator. So if we take our denominator and we set it equal to 0, we can find where that vertical asymptote is. So if we add 1 to both sides, we get a vertical asymptote at 1, x equals 1. And again, where this comes from, where this comes from, this is our denominator. Whoa, ran out of room there. So that is our denominator. We set that equal to 0, and that's how we can find our vertical asymptote. Okay, if we look at the next asymptote, our horizontal asymptote, that's where we have that added value at the end. That's going to be our horizontal asymptote. And we noticed on Desmos that it shifts our entire function up 2 units. So instead of our function now being at 0, we have shifted it up 2 units, and our horizontal line is always y equals, and so it's going to be y equals that value we are adding at the end of our function. So that's our horizontal asymptote. Okay, so we're going to use something a little more than our key points to graph our rational functions, and that's because we want to get a good shape for our graph. So instead of using like our parent function like we've done in the past, we're actually just going to use a traditional table, and we're going to use our asymptotes to figure out what those values in our table should be. So if we go ahead and make our table, I'm going to choose values that are going to be around this vertical asymptote. So I want some on the right of my asymptote, and then I also want some on the left of my asymptote. So we're going to go ahead and put our asymptote in the middle, and we know that's undefined because if we plug in 1 to this equation, we get 1 minus 1, which is 0, and we can't divide by 0. So I'm going to pick 3 points that are less than 1 and 3 points that are greater than 1. And we're just going to plug them in to solve. So we're going to plug them into our equation, like we said, traditional graphing. So I'm just going to show my work down here. And we're just going to substitute in -2 to our equation, substitute in -1, and so on. Maybe I'll show some work off to the side. So if we plug in -2, we're going to get 1 over -2 minus 1 plus 2. So this will be 1 over -3. So my 3's will cancel out. So I get 3 times 1 over -3 plus 2. So this will yield a -1 plus 2 is +1. Now if I plug in -1, I'm going to get 3 times -1/2. So that's going to be -3 over 2 plus 2 is going to be 1/2. So remember, -3 over 2 is the same thing as 1.5 or -1.5. -1.5 plus 2 will get +1/2. If I plug in 0, I get 1 over 0 minus 1. So that's just the same thing as 1 divided by -1. So 3 times -1 plus 2 is -3 plus 2, which will get -1. Then I have my undefined, I have my asymptote, and then I'm going to continue on the other side of my asymptote. So plugging in +2. Here I have 1 over 2 minus 1, which is just going to be yield 1. So I get 3 plus 2, which is 5. Plugging in 3 now, 3 times 1 over 3 minus 1 plus 2. That's going to be 3 times 1/2. So that's 1.5 plus 2. So 1.5 plus 2 is 3.5 or 3.5. And then lastly, I can plug in 4, which is 3 times 1/3 plus 2. So I can see these will cross cancel. I'll get 1 plus 2 is 3. So now we have enough points to go ahead and graph. I'm going to make my coordinate plane, and then I also want to include my asymptotes. So we're going to create our coordinate plane first, then we're going to graph our asymptotes, and that's going to help us to kind of set everything up right. Okay, so I like to, just like we kind of talked about yesterday, I like to include my asymptotes in a highlighter, but you can use a dotted line or just regular pencil. So we have an asymptote at x equals 1. So I'm going to include that here, vertical asymptote at x equals 1. Okay. And then I have my horizontal asymptote at y equals 2. So y equals 2 is right here, and it's horizontal through 2. And now I can plot my points. Okay, so I have -2, 1. So -2 up 1. Then I have -1, 1/2. 0, -1. And then I'm undefined. So this is kind of the left portion of my function, so I can sketch that in. And as a minimum, we want to have 3 points. If you would like to do more, you can. But for as a minimum, we want to have 3 points on either side, because that helps us to get that shape. And then also, in this case, gets us our y-intercept. So those are both things we want to include. Now, if we go ahead and graph the other half of it, we have 2 and then 5, 3, 3.5, and then 4, 3. And again, we know we're going to get really close. I'm going to go ahead and extend my vertical asymptote up here so I can draw my function a little easier. So I know I get really close to those asymptotes, but I will never actually cross them. So when you're sketching your function, you want to make sure that that you're not touching those asymptotes either. All right, so there is our graph of 3 times 1 over x minus 1 plus 2. So this is one form you'll see on your practice. You'll see the kind of written in this form where you can identify your horizontal asymptote pretty easily. But another form your function can be written in, so I'll make kind of another header here. We'll say graphing in the form of f of x equals ax plus b over cx plus d. And so in this case, a, b, c, and d are all just real numbers. Okay, so this is just kind of indicating that these are numbers. So the thing that looks different about our form we have here and our first form is that, notice how we just have our x in the denominator, and we also have this constant added at the end. So in this case, we have an x in both the numerator and the denominator, and we don't have any kind of constants at the end. So we'll still find our vertical asymptote the same way. So if you remember, our vertical asymptote is where where our x produces a 0 in the denominator. So just like before, we had our vertical asymptote where x produces 0 in the denominator. But our horizontal asymptote we're going to find a little differently. So I'm first going to indicate or write down our vertical asymptote. So you're still going to set cx plus d equal to 0. So remember, this is our denominator. That's the same thing. Set your denominator equal to 0. But to find our our horizontal asymptote, what we're actually going to do is, when our degree is the same with the numerator and the denominator, we're going to just divide these values, and that will be our horizontal asymptote. So we'll talk about what will happen if our degree is not the same. But today, your practice will just include functions where the degree is the same. So we have an x over an x, or x squared over x squared. When degree is the same. So to find our horizontal asymptote, it will be equal to y, and then we're dividing these leading coefficients. So a divided by c. So this is how we'll graph, or how we'll identify our asymptotes when we're written in a form like this. Okay, so again, the vertical asymptote is still where the denominator is 0, and our horizontal asymptote, we're just dividing those two leading coefficients. So here's our next example. We have the degree that's the same. So we're going to find our vertical asymptote by setting the denominator equal to 0. So our vertical asymptote will be 1, and our horizontal asymptote is going to be y equals our two leading coefficients. So remember, we have this imaginary 1 in front, or not really imaginary, but invisible 1. So we have 3 over 1 equals 3. So y equals 3 will be our horizontal asymptote. So if we go ahead and create our table, we want to choose 3 points on either side of our vertical asymptote, and we're going to graph both of these. So we'll put our vertical asymptote in the middle. Remember, it's an asymptote, so it's undefined, because if we were to plug in 1, we would get 1 minus 1, which is 0, and we can't divide by 0. So 3 points that are smaller than 1 and 3 points that are greater than 1. And now we're just going to plug in and solve. So I'm going to go ahead and I have my values here. So I'm going to help you so you don't have to watch me evaluate all of them. But you'll do it the same way. You're going to plug in -2, and then you'll solve the whole function. So for the sake of our example, I'll go ahead and just give you our values already solved. Okay. And notice how I'm using fractions, especially for these decimals that are these decimals that do not terminate. So let's go ahead and graph to see what this looks like. So our vertical asymptote is at x = 1. Our horizontal asymptote is at y = 3. So we have -2 and 3 1/3. So notice how now our left-hand side is actually above our horizontal asymptote. So -2 and then 3 1/3. So we're going to go about 1/3 of the way through the box. And then we have 3, so -1, 3.5. We've got that y-intercept. And again, we don't want to touch the asymptote. We're just going to get really close. Whoa, got a little crooked. Okay. And then for our second half of our function, we have 2, 2, 2, 3, 2.5, and then 4, 2 2/3. All right. So when you are practicing with your homeworks, make sure you're identifying both asymptotes. Make sure you're making a table of values where our vertical asymptote is in the middle, and we have at least 3 on either side. We want to work to find that y-intercept, and again, the 3 points on either side help us to get a nice shape for the function. So if you're looking in the textbook, you'll notice they use key points. They have like 1 reference point, but we want more to make sure we get the right shape.